Okay, let me again remind you what we're doing is we're doing point estimation. The first section was devoted to understanding what an estimator is, what's the role of the estimator, or what's the use of an estimator. Then we looked at if we have more than one estimators, then what should be the properties of estimators that we should be looking for. Okay, so we had gone ahead in the first section. Now we're coming back before looking at perfect or better estimators or estimators. Some of them may be good, some of them may be bad. We're not going to talk about that in today's class. In today's class, we'll take a baby step of how do we obtain an estimator to begin with before going ahead and estimating multiple and then looking at which ones are more useful than others. Utna nahi hum karenge. So method of moments is just a 5-minute job. There's nothing special. However, what I feel is I should elaborate a little on the concept of moments. Have you been explained the concept of moments before? Anyone? No one? ठीक है. Okay. GE, हाँ GE starts में हुआ होगा. I'll keep it very short, just because although we're not supposed to do moments here, but since this does involve the concept, I'll very briefly try to explain what this concept is about. Okay, so now we'll speak of population. To begin with, let's say we have a population consisting of these 5 values. So it's a very small population: 12, 14, 14, 17, and 18. And we can put this population on number line like this: 12, 14, 14, 17, 18. Yeah, this is 0. Yeah. Okay. Now, this is a pretty small population, so one can just look at it and understand where this is. This is taken to be a small for simplicity. If it's pretty large, then it becomes very difficult to even see. If you have a million values, then you can't really see what values. Then you need summary measures for obtaining information about population. This is small, but for large populations, we need summary measures. Okay. E of x raised to power k, for k is equal to 1, 2, 3, is called the kth moment, and this can serve, or I should say these can serve as summary measures for a population. Okay, so e raised to power x, and let me also say these are crude summary measures. E of x is the population mean. What does the population mean? Tell us. Average distance from 0 or the central location. of where the population is on the number line. Okay. E raised to power x for this is 15, somewhere over here. अच्छा है, पता लग गया कहाँ पे है. This is 0. Now we have another population. 15, 15, 15, 15 and 15. We have 12, 14, 17, 18. And we have 15 over here. The summary measure that we have is same for both. It's 15. Okay, so the first summary measure that we have tells us something, but that something is not enough for us to be able to differentiate various populations. Yeah. We can now look at, or we should now look at the second crude moment. Which is E of x square. This is 229.4 for first population, 225 for second population. Okay, now you can see, okay, or from basic arithmetic, we should know that if the second crude moment is higher, that means the population is more spread out. These values 17 and 18, which are above the average, they inflate the second crude moment. If we square them and add them up, then that number will be inflated uh, from the larger numbers. It will be deflated from the smaller numbers, but the deflation from smaller numbers is not enough to offset the inflation from larger numbers. This second population, all 15, there is no inflation, there is no deflation, so we have this 225. So the larger the second moment is, we know that the population will be more spread out. Okay, but there's a problem even with this second moment. The information provided, this info on dispersion is still crude. If on the number line we have these two, let me use colors. So red and green. The two distributions here have a different location, but the distribution is same. Okay, the spread of the distribution is same for both. The first moment will be different. Okay, that tells us where the average is. It should be different. The second moment doesn't really give us this information that the distribution about mean is same. The spread of this, if we put it this way, this is similar. E raised to power x square here would be much higher than e raised to, oh sorry, not e raised to power x. Expected value of x square for the green distribution would be much higher. Okay. Now that is a problem. We should have, or we should be able to get a summary measure which tells us, okay, they're located at different places, but within their vicinity, they're similarly distributed. So we can refine the crude moments to get better summary measures. Okay, the subscript 1, 2, 3, 4 are to denote that we have first, second, and third moment. The prime on top is to denote that we have crude moments. Okay, first one gives us good information, second one not so, third and fourth in crude form are not useful. But if we can refine then this coefficient of skewness, coefficient of kurtosis, the second one is okay. Now when you were taught statistics first time, I suppose in 11th, you were straight away taught standard deviation होता है, variance होता है, ऐसे ऐसे कर लो, इसको सम कर दो, स्क्वायर कर दो, कैलकुलेट कर दो, बहुत अच्छी इंफॉर्मेशन मिलेगी. Okay, so you are parachuted right in the middle of theory of statistics. Here I am taking you in steps. First we got this, then we saw that नहीं नहीं ये तो इतना यूजफुल नहीं है, इसको कुछ ट्यूनिंग करके रिफाइन करते हैं. So we moved from here to here and figured out that okay fine, इस फॉर्म में ये अच्छा इंफॉर्मेशन देता है. Okay, something of that sort. Variance, if we look here, the variance of the green and the variance of the red distribution should exactly be same. Mean दोनों का यहाँ पे बीच में है. The distance, these distances are same from the mean for all observations. So squares of these deviations will also be the same, and the expected value of these squares of the deviation would also be same. For kurtosis and skewness, we have this. Now I'm writing the formulas in this form, not the expected form. X minus mu raised to power 4 into sigma 4. Okay, all these coefficients give us precise information which tells us very neatly what the population looks like. Okay, so we have refined moments. So these parameters that we study in statistics are actually derived from moments. Crude moment refine करके ऐसा आ गया. Is this fine now? Moments, that's all I will do for moments in this class. Okay, now let's move to method of moments. For obtaining parameters. Now, to begin with, you will feel slightly uneasy with this theory. This is, again, statistics as it is really required in modern world, not just economy, but even otherwise. Now, claim up front, or rather, telling that no claim is being made about bias or unbiasedness of obtained estimators. Okay, you are already told that S square, or when we divide the sum of deviations of sample observations from sample mean by n minus 1, you get an unbiased estimator. If you divide by n, you get a biased estimator. Okay, now we're just moving away from that we already know from theory which has been developed previously. Right now we're trying to develop स्टेज बाय स्टेज. तो हमको नहीं पता अभी कौन सा वाला बायस्ड होगा कौन सा अनबायस्ड होगा. वी ओनली नो दैट दिस इज अ मेथड which can help us obtain an estimator. After obtaining the estimator, we'll worry about whether it's a biased estimator or unbiased estimator. Now, since we will be trying to, oops, not parameters, estimators. Since we're trying to get estimators, which will be from the sample data, we need to define moments for sample and population separately. Okay, so we have some population, either a given PMF or a PDF. Expected value. Okay. Yeah. So see here, I'm using a E. I'm using sigma, but dividing by capital N. That means it's for population. Now, either I can use E here or sigma x raised to power k by uppercase N. Both is the kth population parameter, population moment. Crude. Sigma x raised to power k divided by smaller case n is the kth sample moment. Crude for k is equal to 1 to what do we do in method of moments? Simply we equate the population moments with sample moments. Okay. Now the first two moments, the first two parameters that we're going to try to estimate are themselves moments, one crude, one refined. So ठीक है, moments ही estimate करना है, population तो sample कर लिया, but we'll do an example in which we can still use the method of moments to try to estimate parameters which are not themselves moments. So moments estimator of population mean. Okay, population mean is itself the first moment. So okay, about notation, we're trying to get a estimator for population mean denoted by this symbol mu. So we use the same symbol, put a hat caret on top and equate it with the first sample moment. आ गया. Because theory has already been developed, we know that this is an unbiased estimator and it's also an efficient estimator. Among all the estimators that are available for population mean, this one has the smallest standard error associated with it. Okay. Moments estimator of population variance noted by sigma square. ठीक है जी. We're trying to get an estimator for sigma square. We just use the same symbol, put a caret on top, and we equate it with the second sample moment. Okay, here there is an element of further let's say substitution, because we need sample mean, which itself is a estimator of population mean. This can further be denoted like this: sigma x by n square. Okay, now again, since from the theory developed earlier, we know this is a biased estimator of population mean, population variance. Okay, like I said, we're not in the perfect world here. There's no guarantee that we're going to get unbiased estimators. In fact, it will be rare if we get unbiased estimators. Now, these two were moments in themselves. Let's see a case where we need to estimate a parameter which is not a moment. Okay, so we're given a sample from a population which is exponential, and the only parameter of exponential distribution is lambda. Equate first population moment with first sample moment. This is the first population moment. This is the first sample moment, and we know that expected value of the random variable x for a sample which is drawn from an exponential distribution. No, not sample. Sample तो ये है. Expected value of a random variable which follows the exponential distribution is just 1 by lambda. This. Now we'll twist it around. But this is an estimator. Okay, if we have sample data and we calculate the sample mean, divide 1 by sample mean, this is an estimator in general. For a particular sample, we'll get an estimate of the population parameter, and so we put a caret on top. Okay, so we see here the example that method of moments can be used to estimate parameters which are themselves not moments, either in crude form or in refined form. What have we done? We have estimated a parameter which is a crude moment. Then we estimated a parameter which is a refined moment, and third we estimated a parameter which has nothing to do with moments. That will be all for today.